Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Why don't we get started? So today we have Adrian Castle from ENS. It's graduating this year, supervised by Rick Kenyon, who's at Brown. So he's going to talk to us about random curves, Laplacians, and determinants.
Okay, thank you, David. Hi, everybody. Okay, so in this talk, I will be talking mainly about loop-raised random walks in different aspects of it. So let me just, so that everybody is aware of what we're talking about, just recall the definition of loop-raised random walk. So it's random simple path that was introduced by Greg Lawler in the 80s. And this is a sample path on a Z2 with a very small mesh size. And the construction goes as follows. You take a random walk, started from some vertex. And each time you create a loop in the path, so a self-intersection, you erase this loop. Start again from the point you just erased the loop from. Continue the random walk, and so on. So of course, in order to finish this procedure, you need to specify some kind of boundary. So either you can have a target vertex and you will kill the random walk when it touches this vertex. So you can do this on any finite graph, or you can imagine, for example, here in Z2, having a very large box starting at the origin and stopping the walk when it eventually touches the boundary. So that's a loop-raised random walk. So in fact, loop-raised random walks are closely related to uniform spanning trees of graphs. So I will just recall that right now. So this is a sample of a uniform spanning tree on a finite square grid. And it was shown by David Wilson how to sample such a uniform spanning tree from a loop-raised random walk. And the way it goes is as follows. Well, suppose you want to, you pick some vertex in the graph, and you want to sample a uniform spanning tree rooted at that vertex and oriented towards it. Well, the way it goes, this is so David Wilson's algorithm. You pick any vertex which is not the root. You start a loop-raised random walk which ends at this root. And now you keep this first simple path you just created. And now you pick some vertex that is not already on this branch you just created. You do a loop-raised random walk killed when it touches the path you kept at the first step. And you go on until every vertex is covered. So by construction, this will yield a spanning graph, which is a tree. There are no cycles. And David has shown that this is the uniform measure on all spanning trees. Well, oriented, but then you can forget the root, forget the orientation, and you get a uniform spanning tree. Now, okay, so I want to introduce just now a slight variation on Wilson's algorithm, which is that we are not going to erase all loops that are created, but we are going to keep them with certain probabilities. So let me just use this notation. So we pick some finite graph, and I denote alpha to be a function with values in 0, 1, which to any cycle in the graph associates some weight. So, and now we can also put some, of course I didn't say, but Wilson's algorithm work for any conductors biased random walk on the graph. So imagine you have some positive weights on the edges. You perform random walk proportionally to these weights, nearest neighbor of random walk. Well, if you do this, you will obtain a spanning tree with weight proportional to the product of the edge weights. Now, in this slightly different version, what I want to introduce is a probability measure on cycle-rooted spanning forest, which will have a weight proportional to product over the edges of the conductance times the product over the cycles of a certain weight. So let me, if it's not familiar to anybody, to everybody, what a cycle-rooted forest is, spanning forest, sorry. So it's this object here. So you have an underlying square grid. A cycle-rooted spanning forest is a spanning subgraph, and it contains cycles, but in a very specific way, namely that each connected component contains a unique cycle. So you can see them pictured here. On the right, you have a particular case of cycle-rooted spanning forest where there's only one, it's connected, so we call this a cycle-rooted spanning tree. Now, the algorithm of Wilson I just presented for uniform spanning trees generalizes really quite easily to this setting. In fact, in that case, you don't even need to specify any root, and the algorithm goes as follows. So suppose you want to sample a cycle-rooted spanning forest, which has a weight proportional to this factor. So this is product over the edges of the conductances times the product over the cycles in the cycle-rooted spanning forest of their weight.
I'm sorry, tau is a union of cycles? So what?
Yeah, this is gamma, I think. Gamma is a cycle-rooted spanning forest, so it's that. Okay. So it's a union of disjoint cycles, plus each cycle has a tree rooted on it. And the algorithm goes as follows. I mean, I wrote it here, but I will explaining out loud. So you don't fix any root. We're going to sample an oriented CRSF. I will say CRSF for cycle-rooted spanning forest. Oriented in the sense that the branches oriented towards the cycle, and the cycle has some orientation. Now, how does it go? You pick any vertex from the graph, and you perform a loop-erased random walk. Perform a random walk biased by the conductances. Now, when you construct a self-intersected loop, in the usual algorithm, you would just erase it. But here, we're going to flip a coin with bias, with winning probability alpha of gamma. And if it turns out the outcome is positive, we keep the loop. So let me just so you pick some random vertex, you do the walk, you make some loop, you flip a coin with, and you keep this loop with probability alpha of gamma. This is the loop gamma, and you flip a coin with bias alpha of gamma. Now suppose the outcome was that you keep it, so this is your first step of the algorithm. Now you pick some vertex which is not already on this path, and you do the same thing. So maybe you will create some other loop, you will flip the coin, and it will say that you have to erase it. Okay? So you continue, and maybe eventually you will touch this first part. So now you just keep that like that. It will be rooted on this cycle. And so you go on until all vertices are created. So sometimes you keep cycles, sometimes you erase them, and you will touch something which was already created. And what you see is that at the end, you have exactly a cycle-rooted spanning forest, which is, if you will, oriented, but this is not important. And if you follow Wilson's proof of Wilson's algorithm, basically you see that it samples exactly the measure I had on the previous slide. So this measure. Okay. So now I want to talk. Okay, so what we have just seen so far is that so loop-erased random walk is related to uniform spanning trees, as was already known, and it's of course with this modified version also related to the cycle-rooted spanning forests. So in a way, but the difference between the two approaches is in the first case you only have simple path. They're not closed, and here the property is that we really construct certain loops, and we may see them as, if we want, excursions of the loop-erased random walk, right? Because whenever a loop is kept, of course, it's not just a simple random walk along this curve. But each time you may have created some loops that you have erased, etc. So it's a different kind of random path. So in a way, this correspondence will enable to study, well, either the trees using the loop-raised random walk or the loop-raised loops using these trees. And I will show, this will be the topic of my talk right now. So I want first to concentrate on this special case where you have only one connected component. Well, a way to achieve such a measure is to take, so let's forget for the moment about edge conductances, we'll just take them to be all one. And now take for any loop the same weight, which is some very small parameter alpha, which we'll suppose tends to 0. Well, if you are on a finite graph, then if alpha is very small, you're likely to keep only one loop. Basically because if you had k loops, the probability of having k loops would be proportional to alpha to the k. So if alpha is very small, you will keep only one loop. And in fact, you will have the uniform measure on cycle-rooted trees with so only one loop. So I want to talk now just a little bit about this uniform cycle-rooted spanning tree. So finite graph, uniform measure on cycle-rooted tree, which is, I mean, we can also call it the unicycle, uniform unicycle. So, okay, so that's one. Okay, so this is quite a dense slide, but it recalls a different result that I will now explain. So this is joint work with Rick Kenyon and Wei Wu from Brown University. So let me just explain briefly the notations. So here so you have square grid, triangular grid. So suppose you have some infinite periodic grid. So we will just suppose for the moment it's the square grid, but the two other grids will work too. And we take some large box of size n. Now L, so we will look at the uniform measure on cycle-rooted spanning trees of this graph. I can call this graph Gn, and we have the measure Pn uniform on CRSTs. So L is a random variable equal to the length. So when I say length, just the combinatorial length, number of edges of the cycle. So I have somewhere this random cycle. So L is the length. A is the area. So area just means for me the number of faces. We have a planar graph, so the number of faces inside the loop. So the results that I present on these slides concern the expected length, the expected area squared, and I will talk afterwards about the higher moments of the area. So let me start by explaining the first two lines, which are not due to me. But okay, so let me just first explain. Okay, let me first explain the second line. So in a paper by Yuval and Lionel Levine, they have shown that the expected length of the uniform unicycle is related to some constant psi that they call the looping constant. At least, okay, I should explain what this means. This is actually an equality asymptotically. So they have shown, and I will explain in a second how, that for Z2, if you take now n to go to infinity, the expected length tends to 8, the integer number 8, which is a bit surprising. And I don't think we have already a good explanation as to why this is rational or even integer, but it's that. And roughly, to explain how the arguments goes, so what is this psi? Well, psi is some constant that depends on the lattice, but is given by the loop-raised random walk. So suppose you fix the origin here 0, you're on this large block n, and you take a loop-raised random walk killed on the boundary. Now you can ask the question for a fixed n, what is the expected number of neighbors of 0 on this path? So it's a simple path, but okay, you can go to this neighboring vertex like that. And so, I mean, you will have only one neighboring vertex, but you can go to it just directly like that, or by doing some loop and going to it afterwards. So it's not obvious what the expected number of neighbors of the origin is in this loop-raised path. But it turns out that as n goes to infinity, this has a limit, which is xi, the looping constant. And David Wilson and Richard Kenyon have shown that for these different grids, well, xi is equal to 5/4, 5/3, and 13/12. Now, how did Yuval Perez and Lionel Levine relate this to that? Well, I don't have time now to explain it all, but it goes through the burning bijection of Dar, which relates uniform spanning trees to the abelian sandpile, and then uses some convergence for the abelian sandpile by Ethereal and Yarai. And
sorry, what was delta though?
Oh, I'm sorry. Yes, a delta is the a degree of these regular graphs. So yeah. So yeah, okay. So this proof of convergence was done. At least a paper can be found for the squared grid, but I mean. So I think David Wilson has work in progress that it works for the other grids, and therefore using the same argument as in Perez and Levine, we can derive these quantities. So it's kind of interesting that also in these other grids you get integers, and which are actually equals to twice the degree of the dual graph. Well, okay, that doesn't that much, but. So, I mean, this definitely requires some explanation, but we don't know for the moment. Okay, so that was for the expected length. So, you might think that if this random loop has finite expected length, well, it could be the same of the area, or not, and turns out not to be. So, in fact, the area somehow has a heavier tail. So, let me just explain. So what we have shown is that, I will just talk, for example, about the square grid. I mean, the other cases are similar. The expected area on the box of size n grows as log n. And we have the explicit factor. It's 4 by log n. And now the expected area squared grows as n squared. And the constant is some explicit constant, which involves this this number. I will talk about it in a second, but just notice that so the constant in terms of, in front of the leading term is something that is lattice dependent, so these numbers, times something that just depends on the domain. Okay, I understand why you might be surprised. I didn't explain at all what is D. I'm sorry. So okay. Actually, to compute exactly these constants, what we have used is some, of course, we're looking at an infinite volume limit. But since we wanted to convert some kind of discrete Riemann sum to an integral, we actually looked at the scale version. So the way we did it is you take some domain in the plane, and now you push in the square lattice, 1 over n. So each time this will define you some graph, Gn, which just lies as a discrete approximation of this domain. And we may define the same measure, the uniform measure on the unicycles, compute the length and the area. When I say length and area, it's always the combinatorial one. I'm not talking about the the Euclidean one, which of course will tend to 0. So, but if we have sort of this sequence of graphs that have this boundary at infinity, in the sense that when they are rescaled, they approximate this domain, then the constant in front of the leading term of the area squared is given by this, this quantity. So, so actually, so this quantity, you can, so g of zw is the Green's function on the domain with directly boundary conditions. And so you can just think of this quantity as being the mean expected exit time of Brownian motion from this domain. That is, you take a Brownian motion started at some point z, then you integrate the time it is spent at w over all points on the domain. So this will give you the exit time of the domain. So Brownian motion killed on the boundary. And now you average this over all z's. So this will give you the mean expected exit time. And so here are a few examples. So for the disk, so this quantity, at least with this rescaling, is something which is scale invariant, rotation invariant, translation invariant. And it is maximized for the disk. So for the disk, it is worth 1 over pi. And now for a rectangle with aspect ratio tau, it's given by this, for example. So this this series. Just a small comment is, I mean, one way to see that it is maximized for the disk is actually to relate this constant to this, what I called here, rho of d. And so there's a beautiful short paper of Polya from the 50s where he computes this quantity, which has a mechanical interpretation as being the torsional rigidity of some metal beam of cross-section d. So you take a domain d cylinder, and you ask about the torsional rigidity of this. This turns out to be the quantity expressed in terms of a minimization PDE problem. And by using some symmetrization, he shows that it is maximized for the disk. So it's kind of interesting. Now, just one should talk just a little bit about the proof of this result. So I explained these previous works. Now, how about these two? What I call here critical weight is something that comes from the scaling limit approach. So in the scaling limit approach, what we're going to do is that we're going to express these quantities, expected area squared, in terms of Green's functions on the graph. And now here I have used the continuous Green's function on the domain. So what we have actually used is some convergence of the discrete object when rescaled to the actual continuous object. And this requires that harmonic functions converge to continuous harmonic function, and then you have to weight your graph with certain isoradial critical weights. And turns out that for these grids, it is given by these numbers. And okay, so this is why I wrote down these numbers. Now, a word, maybe now I will explain a little bit about the proof. So let me start with the area. So I'm just going to consider a case of a large box of size n. And actually, the simple observation you can make is that if you're looking at a cycle-rooted spanning tree on this graph, and now you take its, which is with free boundary conditions, it's really, and now you take the dual planar graph. Well, this is going to be a two-component forest which is wired on the boundary. So let me just draw. If I have here a cycle, some branches free on the boundary, and now I take the planar dual, this will be some tree inside and some tree outside which is rooted on the boundary. So in fact, a way to answer, okay, and now, for example, if we want to compute the expected area, we just have to sum for the cycle rooted tree over all faces the probability that this face lies inside the uniform CRST, right? This is just the expected number of faces that are inside. This is the area. So in fact, we need to know these probabilities. So we want to know, given a face, what is the probability that it lies inside the circle? Well, if we take the dual approach, it's just asking, well, if we pick some face, so it's a point in the dual graph, what is the probability that it lies in this floating component? So the component of this bi-tree, which is not rooted on the boundary. And then we can use some electrical network theory or some results already from Kirchhoff about the number of spanning trees, and we can show that the probability that f lies in this uniform spanning tree is equal to the so I will denote kappa the number, well, okay, I will just write number of spanning trees of the graph divided by the number of cycle rooted spanning trees times the Green's function on the dual graph, so I will put a star, with Dirichlet boundary condition on this outer vertex evaluated at face F. This is in fact the electrical resistance in a network between one point F here. I mean, if you put unit resistances on all edges and ask what is the resistance between this point and the outer vertex. So we obtain that. And actually, when we consider, so now how, okay, basically what is the asymptotics of this? Well, this Green's function evaluated at the same point for almost all faces will be something like 1/2 pi log n. Now, this ratio, number of spanning trees divided by the number of cycle-rooted spanning trees, is actually related to the expected length of the cycle-rooted spanning tree. So, and this was shown to converge. So actually, this will be roughly. Let me get it right. 8 over n squared. Okay, the reason for that, I will just say it in a few words, is that if you take a uniform spanning tree and you add some random edge, well, you will obtain a cycle-rooted spanning tree. But it will not be the uniform measure, but it will be biased by the length of the cycle. And therefore, if you compute the number of spanning trees times the number of edges which are not on the tree and divide it by the number of cycle-rooted spanning tree, you will get exactly the expected length, which is 8. Okay, so using this result, you obtain that roughly this will be 8 over n squared 1/2 pi log n. And so this is now 4 over pi, that's just 1 over n squared log n. And now you sum over all the n squared faces, and you will get that the expected area is 4 over pi log n. Now, for the case of the second moment of the area, it's a bit the similar approach. We just write that the expected area squared is a sum over all pairs of faces of the probability that both faces lie inside this CRST, the cycle. And now the result is that the probability two faces being inside CRST. Well, how can we compute that? This is the probability. We're going to condition on one face to be inside. So let's take f and f prime. Let's suppose f is inside the cycle. Now, what's the probability that f prime will be inside? Well, using either using the Wilson's algorithm or some other technique, you can show that it's the probability that random walk started at f prime touches f before it hits the boundary. And this is just a harmonic function which is worth 0 on the boundary and 1 at f, and which you evaluate at f prime. So the conditional probability here will just be this harmonic function, which you can write in terms of Green's function as this ratio of g star evaluated at f prime divided by g star at ff. Now, using the result we previously had for probability of f, which is that it's this ratio times that, there's a simplification, and you obtain number of spanning trees, number of cycle-rooted spanning trees, g star of f prime. Now, using the same result as before, this will be that. And now, using some care and the convergence I explained earlier, I mean, taking care of these critical weights, you can show that this Green's function will be an approximation of the continuous one. And since you're now summing over all pairs of faces, this will be like a Riemann sum for the integral, which is written here. OK. So now, OK. OK, so let me just go a bit more quickly now. It turns out that for higher moments, this kind of simple bijection by relating the cycle-root spanning tree to its dual, which is just this tree with two components, and then using the simple electrical properties, turns out to be much harder if you want to take more points into account. So, for example, if I wanted to know what's the probability that 3 specified faces are inside the cycle, which would be a way to compute the third moment, well, this turned out to be, at least we don't know how to do it intractable. But via some other method that I will now introduce, we were able to show that the kth moment grows like that. And this is just a constant that depends on k and d. So these techniques I will now introduce is more related to a scaling limit approach. So we will now not only consider this uniform cycle-rooted tree on the graph, but rather try to compute some scaling limits of CRSFs, cycle-rooted spanning forests. So, okay, let me show some samples, and then I will introduce what this is and how we should compute them. So, okay, so these are different surfaces. First one is a sphere with its usual metric, some other curved surface. This is a hyperbolic ball, and this is a flat torus, so with these sides identified. And I represented here only the loops of certain cycle-rooted spanning forests, which will be weighted in order that they are macroscopic, and then we forget about all the branches that cover all the graph. So I didn't say, but we will consider some graphs embedded on these surfaces, which approximate them in a certain way. Okay. So let me now go to this topic. For this presentation, I will consider only one case, which is we take some domain in the plane, which is topologically non-trivial, I mean non-simply connected. So there are some holes. And we approximate it by the square grid, 1 over nz2. So this will be the graph Gn. And this is the surface sigma. Now, for each n, we will consider Pn to be the uniform measure on incompressible cycle-rooted forests. What is incompressible? It means that all the cycles of the cycle-rooted spanning forest, so like on the left, must be non-contractible. So they have to enclose at least some of the holes. This will ensure that they are macroscopic when we go to the limit n goes to of mesh size going to 0. So this is the measure we consider, and we can view it as a measure on the space of multicurves of the surface, which are just finite collections of continuous curves, which I will suppose in this case incompressible as well, so non-contractible. So maybe something like that, something like that. And so if we consider for the surface sigma omega to be, so omega k means the multicurves with k curves. So this is naturally endowed with a structure of metric space. And we can consider F to be its Borel sigma field. And I will define the two next notation in a second. Okay, so that's, for example, what would be an incompressible CRSF on such a surface. And this is the theorem I want to prove. So I want to prove, so this is joint work with Rick Kenyon, that there exists a probability measure P, so on the space of multicurves of this surface sigma, such that the sequence Pn converges to P. The idea of the proof is uses a classical paradigm. So we will show tightness of the sequence of measure, and then show convergence for some specified events that form a determining class for the sigma field. And then by using Prorov's theorem, this will ensure convergence actually to the probability measure.
So can I just make
yes.
Just once more that I understand. So the condition is every cycle is non-contractible.
Yes. Yes.
So
yes. Yeah. I'm sorry. I didn't.
you could have many cycles around one, for instance, or you could have just one cycle around one hole.
Yeah. Certainly. Yes. The number of cycles is not conditioned. I mean, it could be one. It could be more.
But you could have to prove them chronologically equivalent.
Yes. Certainly. Yes. That's the only condition is that it's uniform and on the space where the cycles are non-trivial.
You said it clearly. I just want to make sure it has sunk in to my brain correctly.
So I will explain the second point in a bit of detail, and so let me explain what are these cylindrical events which form a determining class which we want to compute. Well, basically there are events like this one. So let me explain what this means. Well, we take the surface, and now we will. Okay, one approach to this to the topology of curve is to say, well, if we know the topology of the curve with respect to, I will add some blue holes in the surface, and then not ask precisely how the random curve behaves on the surface, but just what is its homotopy class with respect to this additional punctures. And if the idea is that this will generate the Borel sigma field, because if you knew the probabilities for all these events, and let's say you take the squares blue to be on a dense subset, the countable subset of the surface, you will actually get the precise information on the topology of the curve. So basically, we're interested in what I called here lamination. And lamination is just a word to say isotopy or homotopy class of multicurves with respect to a topology. So I fix now some blue squares in additionally to the black squares. And the cylindrical event is so E, which depends on the blue squares and depends on some lamination, so some homotopy type with respect to this topology. And it's just, well, the event that the CRSF belongs to that homotopy type. Now what we want to show is convergence Pn of E. Well, this is E. Well, okay, so we want to show that this converges. Now, okay. So in order to do that, this is where the Laplacian comes into the picture. Okay, I will just recall technology that was introduced recently by Rick Kenyon, which enables to compute exactly this the probability of this event I have just shown. So the idea is that you take a graph and you define a connection on a graph. So I will say SU2 connection on a graph to be the data for each oriented edge VV prime of some matrix VV prime belonging to SU2 matrices. And now the only condition you impose is that on the reverse orientation, it's the inverse of this matrix. So phi V prime V is phi VV prime inverse. And given this data, what you can compute is around any simple closed curve, you can compute the product of these matrices. And this is what he termed in this context the holonomy of the connection on this curve. So this is just mimicking some geometry language, but so holonomy.
This product is the limit as you
described. So this is on any finite graph.
Oh, this is still on
Yes, this is on any finite graph. Holonomy of phi around cycle gamma is the composition of the phi v1, I mean vi plus 1 if the cycle is indexed by vertices vi. Now, okay. Now, Rick Kenyon has proved the theorem, which is that where should I write it? Okay, see, he has shown that you can define a twisted version of the usual combinatorial Laplacian on the graph using this connection. How does it work? Well, usually the Laplacian acts on functions over the graph, just like that. But in this case, the Laplacian will act on. You can imagine that the graph is endowed like it's like a two-dimensional bundle. So over each vertex, you have a two-dimensional complex vector space, and F is now a section of this bundle. And the twisted version is that Laplacian phi of a section is f of v minus phi v prime v f of v prime. And the theorem he has shown is that you can define what is the determinant of phi, of Laplacian phi. Turns out that it's a sum over cycle-rooted spanning forests, product over the cycles of the forest, of 2 minus traced the holonomy around gamma. So when you have matrices that are in SU2, their trace is a positive number smaller than 2, so this is positive. And this is actually a sum over the cycle with the spanning forest I introduced. So note that in contrast with the usual combinatorial Laplacian, which is not invertible on a graph, well, this operator has determinant non-zero whenever there is at least one cycle where the holonomy is non-trivial, not equal to the identity, in which case it would be only 0. Now let me call this function z of phi. Now it turns out that if we impose some condition, there's a natural condition to impose on the connection. This was for any finite graph. But now let me come back to the case of our graph Gn. It's embedded in the surface in the way, so there's some topology. Well, you can ask that the connection be flat, which means that the holonomy around any contractible curve is 1. I mean, is the identity matrix, which means that no contractible curve can count in this sum for a flat connection, because trace will be equal to 2, trace of the identity, 2 minus 2, it will be 0. So if you consider a flat connection, z of phi is a sum over incompressible CRSFs, the same weight, product of a cycle, 2 minus trace holonomy of gamma. Now, there's something even more which is true about flat connections, which is that if you take two curves that lie in the same homotopic class, namely that define the same lamination as introduced with respect to this topology, the trace of the holonomy will be the same. This is just because when you deform, you can write it as a product of one cycle which is contractible and the other cycle. And since the contractible cycles have holonomy 1, it's easy to see that they will define the same trace of holonomies. So in fact, more is true. You can write that this is a sum over laminations, then a sum over incompressible CRSF lying in the lamination. So sum over laminations L, sum over CRSFs lying in this particular lamination L, of a certain function that I will call TL of phi, which is the product over, for any representative of this lamination, it's the product over the cycles of 2 minus trace of the holonomy. So this just depends on the lamination, not on the particular multicurve which represents it. And now, since this, since of what I just said, it means that this can be factored out, right? It doesn't depend on any of the particular CRSF. It's just a T. And now, what is this number? Well, this is the number of CRSF lying in L. But this is the numerator, if you want, of the probability we're trying to compute. Because Pn of E is exactly the number CRSFs lying in the lamination we have chosen L divided by the total number of incompressible CRSFs. So I will write this A of L for this number, and for this partition function just Z0. Now, how to conclude? So, no, I think I wanted to just, well, okay, maybe it's, well, okay, maybe it's, I don't know. It would be easier if we remove it, or, I mean, the last slides are not that important. I mean, if it's easier for you to follow if I write in the middle. Okay. So the question really is to show that this ratio now converges. Okay, so using the technology we've just written, basically AL is the coefficient of the TL of phi in Z of phi. This is Z of phi. We want the coefficient AL in front of that function. So I think function, because now we're actually not prescribing any particular flat connection, but we're just looking at this as a function over the space of flat connections on the graph. And so now this is a theorem from Fock and Goncharov that these functions over the space of flat connections are actually linearly independent. So asking for the coefficient AL is just asking for the coefficient in this basis expansion. So if I just use the usual dual notation, I mean, we're just asking for the coefficient of TL in Z of phi. And this is the dual of TL on the vector space of functions over the space of flat connection, and divided by Z0. Now by linearity, this is TL star of Z phi over Z0. Okay, so this is exact computation. It just is done on the finite graph Gn. But now we want to show the convergence. So in fact, it was proved by Rick Kenyon that this ratio converges. So he has shown this using some discrete complex analysis techniques. So we know that the what's inside converges, and now we need to show some continuity of this operator. But this is not obvious. But we were able to show this. And by combining these two facts, well, you obtain that this has a certain limit. So this is how you construct this limit. Now let me say just a word about the first. So tightness. Tightness essentially means to show that the curve remain simple and that they don't have, for example, double points and this relies on previous work about the loop-arrays random walk, because as I explained in the beginning, these CRSFs can be sampled by means of Wilson's algorithm, and much work was done by Eisenman, Borchardt, Newman, and Wilson, then Schramm, then Schramm-Loewner, Werner, to show that loop-arrays random walk converges to SLE2, and we use these tightness results in here. So this is for this convergence. Okay, so this example is just to show that this is an incompressible CRSF on an annulus, and we can hope it has some links. So we do not know of direct description in the continuums like there exists SLE for SLE2 for loop-arrays random walk. But I just want to point out that in this example, the dual of this incompressible CRSF, which is conditioned to have only one loop, is exactly a tree which is rooted on this and this. And I mean, since okay, in this example, I think it appears that there should be some close link to SLE, but it's not. It's just a heuristic for the moment. Okay, so there are some other weights corresponding to these pictures that I have shown you that we can define. And actually, they require some more technicalities to show the convergence. We don't know of any more easier approach. So one of them is to look at a measure on cycle-rooted spanning trees, so only one component. But if you take the uniform measure, of course, it will not have a scaling limit. We have seen before that the expected area it will be very small if you look at the Euclidean area.
I missed something. I thought the construction of these measures was partly motivated by computing those moments of A to the K.
Yes, so that's exactly what I'm about to say. So in this particular case, it's not the uniform measure on CRST that has a scaling limit, but the one weighted by the square of the area. Turns out that if you favor large loops by pushing them by a factor of the area, you can show that it converges. And now, in order to get the moments of the area, basically this is just a change of measure, and you will see that the k plus 2 moment of the area divided by the second moment of the area is exactly the kth moment of the area for this biased measure. And so showing that this has a scaling limit shows that rescaled by the appropriate factor. It has a limit, and then that's how we get the moments. So it's a bit, I mean, compared to the first cases, it's much more intricate. So there might be some simplifications, but we are not aware of them.
Not the first line of argument that comes to mind.
No. And actually, we didn't think of it, we didn't introduce this to prove this. It just realized that it was a consequence.
So you get the moments inductively. You get k plus 2 goes to k. And
No, actually, just directly, you write that. So this is for the uniform measure. E k plus 2 divided by A2. So this one we know it.
Yeah.
And now this is the expectation for the weighted measure of A to the k. Okay, but now A to the k is just the combinatorial. But if I rescale by n squared under here, this will be a Euclidean error. And so this has some, so I should multiply here. And now this is equal to n squared. So you get that it's this constant times n to the 2k minus 2. So just direct.
Mysterious constant CK or P, do you know?
No, it's just like it's the expected average. Yeah, that's yes, exactly. Okay, so and there are some other measures you can define using, for example, on the sphere I showed you there were two loops. It's because we're not looking only at measures on CRST, but there can be several loops, and they're also weighted as a function of the area they enclose, basically. Now, how much time do I have left? 3 minutes. So I just want, this is my last slide, I just want to make a small comment. So the uniform spanning tree, when you view, okay, so this is not a uniform spanning tree, but think of a uniform spanning tree. You can view it as a point process on the set of edges of the graph, right? It's just a bunch of edges on the graph. And it turns out, this was proven by Burton and Pimentel, that for the uniform spanning tree, it's a determinantal process in the sense that the marginals, so the probability that certain edges are inside, this can be computed as, so that k edges are inside, it's a k by k minor of some kernel. Well, it turns out that for these measures on CRSF, they are also determinantal processes viewed as point processes on the edges. However, it seems that they are slightly in a more general class because, for example, if I want to look at this particular picture, so namely this is a measure on CRSF, but which is conditioned, for example, it doesn't enclose any of the holes, it has to enclose at least a more complicated topology. Well, I can construct such a measure basically using some connection as here, and then the determinant of the Laplacian will be a partition function for these. So if I take a connection phi such that the holonomy around any hole here is trivial, but the holonomy around a more complicated path is not. So this relies on the non-commutativity of the SU2 matrices. And it turns out that this process can still be thought as a determinantal process, but its kernel now takes SU2 values, or quaternion values, non-commutative. And in fact, so I have looked a little bit at these processes, and they share most of the properties, known of the determinantal processes, because they're basically kind of algebraic. For example, the number of points in a domain is a sum of Bernoullis, etc. But I haven't been able to make use of it, but they seem to belong to a slightly more general class, because, for example, this process cannot be written as a usual symmetric determinantal process. Okay, well, I think I'll stop there then.
So even though this is not, you said, the determinantal process in the usual sense, you still get things like negative association between variables?
Yes.
That's
Yes,
from
yes,
this
yes.
more general notion.
Yes.